Hello again. Welcome to the third segment on data analysis. In this segment, I'm going to be talking about time to event endpoints. We've described models for measurements, we've described models for categorical data, and now we'll move to the third most important type of endpoint in clinical trials research. Now, this is an ambitious segment. I'm going to cover a lot of material, and I can't really cover it in the depth that it deserves, that indeed this would be a topic that would require an entire course of 6 to 8 weeks to discuss in adequate depth. But I believe that I can convey some of the important ideas to you, and I can illustrate the use of survival analysis methodology, as it's called, when our endpoint is a time to event endpoint. So let's give it a go. So, of course, in some studies, the outcome variable is the time to an event. We've talked previously about the coronary trial. Recall that the coronary trial had a composite endpoint, and the outcome was the time to the occurrence of any component of the composite endpoint. But in cancer trials, an endpoint might be time to progression or death, so the endpoint would be called progression-free survival. Or if we're studying multiple sclerosis, we might study the time until the patient experiences a pre-specified decline in a measure of functional status. So these would be various examples from 3 chronic diseases where you would have a time to event endpoint. Now, the methods for analyzing this type of data are known globally and collectively as survival analysis, and I'm going to illustrate the components of a survival analysis. Now, survival analysis is most important when the subjects enter at different times and have different durations of follow-up, because that will mean that some patients have, say, years of follow-up, others might have months, some of those patients have events and some do not. So survival analysis will compare the entire survival experience, not just the percentages who remain alive at the end of the study. For example, you could have a situation where the survival distributions are different, but the 5-year survival rates are identical. Let me show you that graphically. Here's an example showing 2 treatment groups labeled A and B, and you can see that Group A has a survival rate that's declining linearly, whereas Group B has very favorable survival experience early, but toward the end of the 5 years has a more intense period of fatalities, so that by the end of 5 years they end up at the same time point. Despite the fact that they end up at the same time point, the Group B, one would agree, has a more favorable survival experience and would be the group that one would like to choose if you had that choice. So, okay, those are the survival distributions. How are we going to estimate those? Well, survival data differ from other types of outcomes. Number one, it's not appropriate to assume normality. Secondly, the observation can be censored. Study follow-up can end before a participant has experienced the event, or the participant might withdraw or be lost to follow-up, again before the event is observed. So we have some participants in our study that were followed for a period of time, but for whom no event was observed. This is what we mean by a censored observation. And our survival analysis has to be able to handle that sort of data. This segment is going to be focusing on 2 main issues. Estimating the survival distribution is my first topic, and my second topic is how we compare the survival distributions in 2 groups. And as otherwise in this course, we're using the 2-group situation as the kind of canonical version. You can perfectly well have trials in which there are 3 or more groups, and all the methods I'm describing can be easily generalized to those situations. So let's begin with a simple example. Consider a study which has K years of enrollment and then continues for an additional K years to follow up the patients for a total of 2 years of study time. And here we see a simple illustration for 4 participants. Participant number 1 is enrolled at the day 1 of the study, followed for slightly more than K years, and then has the event, as denoted by the open circle. Participant 2 is enrolled relatively early in the study, followed until the end of the study at time 2K, and never has the event. So that participant is censored, and we've denoted that by the star. You see the third participant enrolled somewhat later in the enrollment period who also had the event, and the fourth and final of these 4 patients was enrolled toward the end of the enrollment period but followed again until the study ended without ever experiencing the event. So 2 participants have events in this simple example, and 2 are censored at time 2K. So this type of censoring is called administrative censoring. It occurs because of the study design, and it's a typical kind of scenario in time to event data. Now, for data analysis, we want to represent each patient's experience not relative to calendar time, but relative to study time, with the day 0 for each participant being the day they actually entered the study. So now I've illustrated that by rearranging the data for these 4 participants so each participant is visualized as beginning at day 0 study time and followed for up to 2K years maximum. And you see the same 4 participants. The lines representing their total time on study are identical, but now they're rearranged to all have a common start time. Now, I've said that most survival data have incomplete follow-up. We've talked about administrative censoring. When the study has an enrollment period and ends at a fixed date, then patients can be censored because the study comes to its end. But also subjects might withdraw, or they might retract their consent, or they might simply be lost. This is a common problem in most long-term studies, is that some fraction of participants become unavailable or unreachable. And this is a threat to the validity of the study, so that every effort must be made by investigators to minimize these losses to follow-up during the course of the study. Now, the survival experience for each patient is represented by 2 quantities: the duration of their follow-up and their survival status at the end of the follow-up period. That's the entirety of the information we need to do a survival analysis. So now let's introduce some concepts related to the survival distribution. So now let capital T be the random variable representing the time to an event for a randomly selected member of the population. I'd like to define 2 quantities related to this random event T. So f of T is the probability that the event occurs before time little t. That's called the cumulative risk, or simply the distribution function for time to death. But in survival analysis, we more often work with the complement of f of t, what we've denoted here S of t. S of t is the survival distribution. S of t is the probability that the participant has not had the event by time little t. Now, it would be easy to estimate S of t if there were no censoring. We'd simply look at time t, how many participants were enrolled in the study, how many are still alive at time t. We'd calculate that proportion. That would be the estimate of the survival probability at time t. But that's not the type of data we typically have in a clinical trial. We have this problem of censoring. So we need a method for estimating S of t when the observations are censored. Now, this is where things can get more detailed, and where the careful description of these ideas would take us quite a lot of time. What I'm going to do is give you a kind of a conceptual discussion of how to handle this problem of censoring, and then point you to the literature if you want to read in greater detail. And by the way, the book by Friedman, Furberg, and Demetz provides a very nice, very readable discussion of the analysis of survival data. So let's describe the Kaplan-Meier estimate, which is the way we describe the survival experience in a single group. So the Kaplan-Meier estimate actually builds upon classical methods for what is known as life table analysis. It updates the estimate of S of t whenever an event occurs, and the update is based upon the proportion of the study period participants who have been followed to that time point and then who have an event at that time point. And the estimator, the Kaplan-Meier estimator, basically is produced by a successive multiplication of these conditional probabilities representing the probability of surviving each time point. So it's this concept of multiplying the conditional probabilities that I want to illustrate with a simple example. So suppose that we have 100 participants entered into the very first day of a 2-year study. And we'll call those participants group 1. And suppose at the beginning of year 2, 100 additional patients enter the study. We'll call those participants the group 2 participants. And now let's display the survival experience of these two groups of participants. Here we see the group 1 experience. 100 patients entered on day 1. During the first year, 20 deaths occurred and 80 participants survived. So the estimate of the survival probability for that group is 80 out of 100. Now those 80 participants are alive at the beginning of year 2, so we can now follow them for an additional year, during which, as you see, 20 events occur, so that the probability of surviving the second year, conditional on the fact that you survived the first year, is 60 over 80, or 0.75. So those participants give us data for the whole 2 years of follow-up. Now, group 2 can only give data about year 1 because they were only followed for up to 1 year. 100 participants entered at the beginning of year 2. Those participants experienced 25 deaths and there were 75 survivors. So let's combine the data for group 1 and group 2 for year 1. We see there was a total of 200 participants and there were a total of 45 events and 155 participants survived of the 200 who began follow-up in this study. Now let's estimate the survival probabilities. Well, in year 1, we can use the data I've just described. 200 participants entered the study, 155 survived, so the estimate of the probability of surviving to the end of year 1 is 0.775. Now what about year 2? Let's calculate the probability of surviving to the end of year 2 given that you were alive at the end of year 1. Well, the only participants who provide any data about that are the group 1 participants. There were 80 of those, 60 survived, so the estimate of that conditional probability is 0.75. So how do we calculate the estimate of the probability of surviving 2 years? Well, it's this conditional calculation. It's the probability of surviving 1 year times the probability of surviving to the end of year 2, given that you've survived to the end of year 1. So it's 0.775 times 0.75, or 0.58. So now the details of this get obviously more complicated with many events at many time points, but this is conceptually what's going on when you calculate the Kaplan-Meier estimator. Here I've shown you an example, a simple example with relatively few study participants to illustrate what a Kaplan-Meier survival curve can look like. And here you see these points. Each one of these step points represent a time at which an event occurred. And you notice that events occur at different times in group 1 and group 2, and you notice that more events occurred in group 1 than in group 2, but you see that the curve remains constant. The Kaplan-Meier survival curve remains constant during periods when no events occur, and then it steps down each time an event does occur, and the magnitude of the step is determined by this conditional probability calculation that I've been showing you. Now here, returning to the coronary trial, I'm showing you the data in the way they were displayed in the New England Journal article by these investigators. Rather than showing the survival distributions, they actually presented the cumulative risks of the event. And they've shown it in two ways here. The larger panel is using the scale, the y-axis, from 0 to 100. And when you display things that way, you get a good sense of the cumulative risk in the two groups. It's of the order of 12 to 13%, as we'll see. And this is often recommended as a way of giving the proper context for interpreting the survival experience in two groups. And when you display it that way, you see that the curves seem very, very close. However, the investigators also want to provide more detail, so they show us an insert where the y-axis runs from 0 to 20, and now you see some separation. You see that the participants in the on-pump group have a higher cumulative risk, at year 2, at the end of year 1, than those in the off-pump group. And you notice that the separation occurs relatively early, that there's a kind of a separation point really about month 1. So that represents not the immediate perioperative experience, but very early experience in these participants. Now, so that's the Kaplan-Meier curve, and I hope you have a sense of how to construct one and how to interpret one. We'd like to now move on and talk about how to compare two survival curves. We've seen the two survival curves in the previous figure. How do we compare them? How can we test whether they're different? Well, we'd like to build on the methods of life table analysis and develop a method for comparing the distributions. Of course, we could compare the probabilities of survival at a single time point, but we've already explained why that's not a great idea. We'd like to be able to compare the entire survival experience. So let me refer to something which is a common and basic concept in statistical analysis, the so-called Mantel-Haenszel test. Now, to use the kind of Mantel-Haenszel approach to comparing two survival experiences, we construct a 2-by-2 table at each time point at which an event occurs. And here's an example. The subscript J here represents the jth event time. And you see we have the number of deaths in group 1 and 2, and we have the numbers of survivors in groups 1 and 2, and then we have the numbers at risk in each group. Now, very typically, either AJ or CJ will be 1 and the other value will be 0. We might have an event time at which only one event occurs, and that event occurs either in group 1 or group 2. But you will recognize this kind of format from the analysis of 2-by-2 tables. So now, because it's a 2-by-2 table, if the null hypothesis is true, the risk of the event is identical for group 1 and group 2, depends only on the numbers of patients at risk in each group, so we can calculate the expected value of AJ and the variance of AJ. And in the next figure I show that. Here you see the expected value using a normal calculation for a 2-by-2 table, and you see the variance of that quantity. Now, imagine that we have a set of event times, arbitrarily large. How are we going to proceed? Well, what we'll do is sum up the observed number of events in group 1, that's the sum of the AJs. We'll sum up the expected numbers of events, that's the expected value, or E of AJ. We'll take the difference between the observed and the expected, and we'll square that in the numerator, and we'll divide that by the sum of the variances. If the null hypothesis is true, this quantity actually has a chi-square distribution with 1 degree of freedom, so it gives us a simple way of testing for the equality of the survival distributions in the two groups. Now, this test, I call, in fact, Professor Nathan Mantell was the first person to propose this approach as an extension of the well-known Mantel-Haenszel test, but it's more commonly known as the log rank test because there's actually a connection between this testing method and a non-parametric test based on the logarithms of the ranks. As I say here, when there's no censoring, the Mantel-Haenszel or log rank test is actually equivalent to a rank test based on the logarithms of the ranks. So that now gives us a method for doing an unadjusted comparison of two groups. But if you think about what we've discussed for linear and logistic regression models, we'd now like to have a regression model for survival data. And in order to do that, we need to describe how one formulates a regression model in the setting of time to event endpoints. We need a metric that can describe how covariates influence risk. If you think back to the discussion of sample size calculations for time to event data, you recall that there was the concept of hazard. So the hazard is the instantaneous risk of an event in an individual participant. And the proportional hazards model, as it's called, will assume that the covariates act by modifying a shared underlying hazard function. So we're going to write down a model in which there's a part which is common to all participants, and there's a part which is driven and determined by the values of the covariates of an individual participant. So remember that S of t is the probability of surviving beyond time little t, where t is the time of death. So what would the hazard function look like? Well, here is the kind of mathematical definition of a hazard function. If you study this, you'll see it represents the instantaneous probability of an event in the small interval t to t plus dt, given that the participant is alive at the beginning of that interval, at t. So what does it mean to say two survival distributions satisfy the proportional hazards assumption? That is characterized by the assumption that lambda 1 of t, the hazard function in one group, is equal to lambda 2 of t up to a constant multiple k, which is independent of time. Now, more generally, the Cox model, or the proportional hazards regression model, makes this kind of assumption. On the left, we have the hazard function at time little t for a patient with covariate values x. We assume that that hazard function has two parts. It has a first component, lambda naught of t, which is the so-called underlying hazard function, which is shared by all members of the population. And then there's a second part, exponent of beta prime x, which is the multiplicative term which explains how the hazard varies as a function of the patient's covariates. Now, that beta prime x, remember, represents the sum of the covariates multiplied by their regression coefficients. Now, that term, exponent of beta prime x, is always going to be positive, because e to any quantity is a positive number. So that's important because the hazard rate must be a positive number, and so our expression here has the property that whatever the values of the covariates and the regression coefficients, the result will always be a valid representation of the hazard rate for that patient. Now, what is the interpretation of the regression coefficients in these models? Well, the regression coefficient beta is actually the logarithm of the ratio of the hazards for two individuals who differ by only 1 unit in the value of the covariate xi. So if xi is an indicator variable contrasting two groups, then beta I will actually be the logarithm of the hazard ratio in the two groups identified by that indicator variable x sub I. You're going to see an example of this in just a moment. Now, how do we proceed to estimate these quantities? Well, the estimates of the elements of beta, that is the regression coefficients, depends only on the times at which events occurs, not on the actual numeric times, but rather on the ordered values of those times. And estimation actually is a somewhat more complicated business because it requires iterative calculations to maximize what's called the partial likelihood function. And we are not going to try to drill down into the details of that. But the important thing to take away here is the interpretation of a proportional hazards regression model parallels linear regression, but where the regression coefficients are interpreted in terms of the relative risk or hazard. Now let's see how these ideas were applied in the coronary trial. So the investigators tell us that we conducted a time-to-event analysis using Cox regression to report the 1-year outcomes. So that's the context we're thinking about. The time to the first occurrence of any one of the components of the primary outcome was described with the use of 3 tools: the Kaplan-Meier survival curve, the comparisons with between the study groups were performed with the use of a log rank test, and the treatment effect is expressed as the hazard ratio obtained from a proportional hazards regression analysis. Here we see a table from that paper displaying the results of the proportional hazards regression for the primary outcome variable, the composite endpoint. You see that the cumulative risk is 12.3% in the 12.1% rather in the off-pump group and 13.3% in the on-pump group. So you see actually that patients receiving the off-pump strategy had somewhat fewer events by 1 year. And in fact, you see that the hazard ratio is estimated to be 0.91 with a confidence interval that includes 1. So we see that the estimate of the relative hazard at any point in time for the off-pump group relative to the on-pump group is 0.91, 91% as large. But the p-value for that estimate is only 0.24, so that we're unable to conclude that there's a significant difference in the risk of the composite event in the off-pump and the on-pump surgical groups. So what did the investigators conclude? They concluded that 1 year after CABG, there was no significant difference between off-pump and on-pump CABG with respect to the primary composite outcome. They also reported that there were no differences in the rate of repeat coronary revascularization, quality of life, or neurocognitive function. So this was a clinically directive study. In a substantial study with well-qualified surgeons, the investigators found that an off-pump strategy did not result in an increased risk of the composite endpoint, was as successful in terms of the need for repeat coronary revascularizations, that the quality of life experience was similar, and that there was no difference in the groups with respect to neurocognitive function. This means that these two options are available to the surgeon depending upon the characteristics and the issues faced with an individual patient, and that both are viable therapeutic options. So this example from the coronary trial has allowed us to see the three main concepts that we use in the analysis of survival data. The Kaplan-Meier curve for producing a description of the time to event distribution in a single group, the log rank test for comparing two groups without adjustment for any other patient characteristics or covariates, and the proportional hazards regression model, which allows us to extend the concept of multiple linear regression into the setting when we're analyzing time to event data. So this brings us then to the last of the three segments on data analysis and clinical trial, and now we'll be moving forward to discussing the interpretation of the results of clinical trials. Thank you for your attention.